Today we want to do a less important section, actually. We've done most of the important identities in the first couple of sections. Now we want to talk about the product to sum and sum to product identities. The sine and cosine are kind of amazing in this sense. Anytime you write a sine plus a cosine or a sine plus a sine, or a cosine plus a cosine of the same amplitude, you can rewrite them as a product instead. So you can write, it's like if x plus y is equal to x times y, how can that be, right? But it has an identity kind of like that. And here's how you can derive them. I'm going to do some of the derivations because one thing we're about here is trying to be able to prove our own identities, right? When you get out into industry, sometimes you get a complicated expression that needs to be simplified so you can recognize what kind of wave it is, or present it to your boss as simply as possible. One of the things we do to practice for that is derive some of these identities, right? So from our identities that we already have for sum and difference, cosine of alpha plus beta is, recall, cosine cosine minus sine sine. These you absolutely have to memorize for your later classes. These are used substantially in calculus and all other higher math courses. These are very important identities. So are the double angle and half angle identities used quite a lot. Now remember, these get too many to remember, so I'm trying to give you some mnemonic devices, some memory things to be able to figure these out. For instance, if you just replace beta with minus beta in all this, then you get alpha minus beta here. This plus becomes a minus. And you get cosine cosine plus sine sine. Because the sine of minus beta also brings a minus out, right? So you just think about your even and odd properties. Replace beta with minus beta here, then cosine minus beta is same as cosine plus beta, but sine of minus beta, the minus comes out. Remember how we derived that? And you get this identity. So this one is immediate from this one using your even and odd properties. And in some sense, you only have to memorize one of these. Now, what you can do is call these equations 1 and 2. Actually, let's call these A and B. We construct their sum and say that A plus B is cosine plus cosine, that is cosine alpha plus beta plus cosine alpha minus beta on the left, equals, and then these two add together to get two of them, twice cosine alpha cosine beta. But these two cancel, one's minus and one's plus. Right? And now if we divide by 2 and switch sides, we get the following result. Cosine alpha times cosine beta is 1/2 cosine alpha plus beta plus cosine alpha minus beta. There it is. This is called a product to sum identity. We can call this equation 1. Anytime you give me a product of 2 cosines, I can rewrite them as 1/2 the sum of 2 cosines. How about that? Who would ever guess that? Product equal to sum. Similarly, if you take the second one and subtract the first one, B minus A, this gives you, let's see, cosine alpha minus beta minus cosine alpha plus beta, second minus the first. Partly I do these proofs so you can figure these out. I said how you can figure out this one from this one by replacing beta with minus beta. These are hard to remember. These are not used as much. And sometimes the way you do them is to figure them out. You remember this proof almost easier than you remember the identity. So that's part of the reason I'm doing this way. They come back to. So this one minus this one is equal to this side minus the right side minus the right side. And so the cosine minus the cosines cancel. These two cancel when you subtract, and now this one minus this one reinforces, and this time you get twice sine alpha, sine beta. Now maybe you see where I'm going for this. If I have a sine times a sine, I can write it as a difference of two cosines after I divide by 2. So switching sides and dividing by 2, I get sine alpha, sine beta equals 1/2 cosine alpha minus beta minus cosine alpha plus beta. So a lot of times I don't tend to memorize these exactly as they are. I tend to sort of figure them out from this one in my head. And you can do that too, because these are less important identities. I'm going to box them because these are the major results today. I'm also going to say that these equations, the sum to product and the product to sum formulas, I don't think you have to memorize. Memorize all the other ones up to this point. These are seldom used, but you need to know they're there because in certain applications they're important to be able to apply. So I won't start these. I'll say you don't need to memorize them. But look, a product of sine times a sine can be written as a difference of two cosines. Now finally, we can get one more product of sum identities. These are both called product of sum identities because you start with a product and rewrite it as 1/2 of a sum or 1/2 of a difference. You can think of this as plus adding this one and a negative. Furthermore, from your C and D, if you like, sine of the sum of angles and difference of the sum of angles. Sine of alpha plus beta is sine cosine. This one you do have to memorize, plus cosine sine. We already did these. And replacing beta with minus beta in these, you get sine cosine minus cosine sine. Because replacing beta with minus beta makes a minus here. Cosine of minus beta, an even function, the minus goes away, but the sine, the minus comes out. And so you can prove this one from this one just in your head. If you take and add these, you get on the left the sum of these two sines, sine alpha plus beta plus sine alpha minus beta equals, you sum these and they reinforce each other. There's two of them, twice sine alpha cosine beta, but these two cancel. And now dividing by 2 and switching sides, we have this one over here, sine alpha cosine beta is equal to 1/2 sine alpha plus beta plus sine alpha minus beta. There it is. This is the last one. There are exactly 3 usual sum to product and product to sum formulas. We aren't going to do these for anything but sine and cosine. So tangent, cotangent, secant, cosecant, we don't have these. They aren't as useful. But these are very useful in certain applications. But as I say, they're probably the least useful of all our identities. So you don't have to memorize this one either. For instance, suppose I have this. This is what the problem tends to be like. They tend to be exercises more than applications. Suppose I take and want to rewrite the cosine of 3x times the cosine of 5x as a sum or difference. Can I do it? Anytime I have a cosine times a cosine, I can, right? It's right here. By equation 1, I just say, well, this is alpha, and this is beta. This is equal to 1/2 cosine plus cosine. 1/2 cosine of the sum of these angles, alpha plus beta, plus the cosine of the difference of the angles, alpha minus beta. I'll put this over the top just to remind myself. This is what's in the formula 1, right? 1/2 cosine alpha plus beta, cosine alpha minus beta. We're just taking alpha to be 3x and beta to be 5x. So we'll put 3x plus 5x and 3x minus 5x. Evidently, the cosine of 3x times the cosine of 5x can be rewritten as 1/2 cosine of 8x plus the cosine of minus 2x. Well, nobody ever leaves it like this. Can you guess why? That minus sign is extra. It's like leaving 1/2 times 2 out front. It's true, but why would you leave the 1/2 times 2? You don't leave extra minus signs you don't need. Remember that cosine is even. Any minus in here can go away. Cosine of minus 2x is the same as cosine plus 2x. So you usually write the answer as 1/2 cosine 8x plus cosine 2x. This will happen a lot in the answers in the back of the key. You get minus 2x. Why is that there? I didn't get minus bucks because it can go away by the even identity. That's why you have to memorize those. Those are very important. So there's the answer to this one. I can rewrite this product as a sum. What good is that going to do me? Well, like I say, these are not as important to apply as a lot of identities, but it does have this kind of advantage. Just for your interest's sake, like the following note. So 3 product to sum identities, rewriting sines or cosine products as sine or cosine sums for differences. Suppose I wanted to sketch this. How could I do it? I can make a rough sketch in my head without even having to go to the computer. The computer can plot those very well. Even your calculator can do that. You put that in your calculator, you get a pretty accurate plot. But I have an idea what it looks like just from putting it in this form. And sometimes that intuition can help you solve an engineering problem or something. So suppose I asked you to sketch. This isn't in the problem set. I just want to show you one of the reasons this is somewhat useful. Sketch the function y equals cosine 3x cosine 5x. Right? How can I sketch that? One way is to rewrite it using the sum identity, because this looks like a jumble, right? How do I know what a product of these things looks like, right? Well, rewrite it as 1/2 cosine 8x plus 1/2 cosine 2x. And now I have an idea. This is what you'll see done in a lot of physical sciences. If this is x and y, I can sketch each of these things independently because we just did that section, right? 1/2 cosine 2x, what does that look like? It's got amplitude 1/2, right? It's got period 2 pi over b, 2 pi over 2 is pi. So I know what this looks like. I can start at 1/2, and I can go over pi units and find out that it completes a period. So it starts at the top since it's a cosine, and it looks something like this. Right? Goes down to minus 1/2, halfway across the pi over 2. So there's what y equals 1/2 cosine 2x looks like, right? Now I can also sketch the cosine 8x, right? How does that look like? This is also amplitude 1/2, but its period is 2 pi over 8. Its period is 1/4 of this one. So it's 2 pi over 8 is pi over 2. Yeah. 2 pi over 8, pi over 4. There we go. And so this one actually has 4 periods for every period this one has. And so it's going to start at the top, and it's going to go 2 periods just to here. It's going to go all the way to the bottom, down to the bottom, and back to the top, all the way down to the bottom, back to the top. And then 2 more times down to the bottom, back to the top, down to the bottom, back to the top. This is what y equals 1/2 cosine 8x looks like. And what you can do is you can kind of picture that in your head. One of them has 4 times the number of periods, for 4 periods for each 1 period of the other one. And now maybe you have an idea how to sketch it. How do I sketch their sum? What you do is you say, I'm just going to take the green one and wiggle up and down over the white one. So I'm going to add these. I'm going to take the height of this one and the height of this one and put them together. It looks like it's about here, right? I mean, this one's a little more negative than this positive. When they're both positive, I'm going to go up to 1, right? Because 1/2 plus 1/2 is 1. But quickly, this one's going to overpower. And here, this one's more negative than this one is positive a little. Here, I could say, well, it's still a little more negative. And so you get something like this. But what's really happening is something like this. Uh-oh. Oops, I miswrote it here. It's supposed to start up here. Sorry about that. And here are those positive. It probably goes a little higher. Something like that. I don't know the exact graph, but I do know it looks a little like that because what it does is this green one is added to the white one, and so you have a curve that wiggles back and forth over the white one, going up and down 1/2 a unit above and 1/2 a unit below the white one. And so you have a pretty good idea what it does, right? It does 4 periods wiggling up and down for every 1 period of the white one, and you can see that just by rewriting it as a sum instead of a product. Now I know, here's the blue one, is the sum, which is also known as y equals cosine 3x cosine 5x. There's what it looks like. It wiggles up and down 1/2 a unit around this function of period pi. So there's one application. You write a product as a sum, you have an idea what the graph does. Right? But there are other applications too, which we won't delve into so much. Well, if I may, I want to now apply these things to derive some new identities that are the sum to product identities. Remember when we had our double angle identities? We could derive from them the half angle identities by substitution, right? If cosine of 2 alpha was cosine squared alpha minus sine squared alpha, how do we derive the half angle identities? Maybe you remember. You replace 2 alpha with theta, and then this one is 1/2 theta, and this one's 1/2 theta. And with a little more work, we got a trigonometry formula for the cosine or sine of a half angle as a function of the cosine of the whole angle. Right? We found out, for instance, that cosine of 1/2 theta was plus or minus square root 1 plus cosine of the whole angle over 2. But you'd use the double angle identity and let theta equal 2 alpha to derive the half angle identity, right? The idea being if you can do a double angle formula, then you can invert it and get a half angle formula. That's the concept there. We don't need this anymore. Similarly here, if I have a product, I rewrite it as a sum, then I ought to be able to take a sum and rewrite it as a product, right? So from equation 1, let's make a substitution to convert this into a sum to product identity. Well, let's say in 1, let's let x equal alpha plus beta and y equal alpha minus beta. That way this becomes cosine x plus cosine y. Maybe I can get a sum to product identity. Of course I can. What happens then with the alpha and beta? Well, if x equals alpha plus beta and y equals alpha minus beta, you can add those, right? x equals alpha plus beta, y equals alpha minus beta. If you add those two equations, you get x plus y over here equals 2 alphas, because they add, but beta minus beta cancel. So then you divide this by 2, and you get alpha equals x plus y over 2. So if I make the substitution, replacing this with x and this with y, then alpha, this one is x plus y over 2. And similarly, I'll put it on the side here, if you subtract those, this one minus this one, you get x minus y equals, the alphas cancel, you get beta minus a minus beta is 2 beta. And consequently, dividing by 2 and switching sides, beta is x minus y over 2. So this substitution here in equation 1 gives what? I just go back and erase alpha. This was cosine alpha. I'm going to write instead cosine x plus y over 2. All I'm doing is a change of variables from x and y to alpha and beta, right? And beta is equal to x minus y over 2 by the substitution. And now that's supposed to be equal to 1/2. Alpha plus beta was x, and alpha minus beta was y. There it is. I'm going to switch sides. Not call this 1 anymore. We'll say do that to get this. All I did was substitute. You watch there, right? And now what happens? Equivalently, by switching sides and multiplying by 2, multiply 2 and by switch sides, you get cosine x plus cosine y, the right side times 2, equals the left side times 2. Twice cosine x plus y over 2, cosine x minus y over 2. There it is. I can get rid of this box here. I don't want to box this one. That's an intermediate result now. And we'll call this one equation 4. This is a sum to product identity. Anytime I have a sum of two cosines, I can now write it as a product. Right? I can take the product, rewrite it as a sum, and I will fix sum and put it back as a product. There's the proof. You just make a substitution, a change of variables, we call it. Any questions on that so far before I erase the rest of this? That seems like a lot of proofs. It is a lot, but I think it's important to see where these things come from. When I went on to mathematics, this is how I could kind of figure out what they were and how to use them. One of the nice things about mathematics you see here is it's not like one of the abstract topics like history where everybody can put their own interpretation on the events, right? Or psychology where they can understand people's minds in different ways. Psychology is sort of a soft science. It's a lot of opinion, supported with certain statistics and so forth. You try and support your opinions as best you can with mathematics. Then there are harder sciences like physics where all the models you put in there have mathematical equations for them, but it's still the rubber meets the road. Is the equations you're using really matching reality? You know, you see it over and over in the experiment, it seems to, and then you always have to go refine your model. That's what they found modeling the atom, for instance. There was the Rutherford model of the atom where you have the nucleus and the electron goes in a big circular orbit around it, or maybe an elliptical orbit. And then they thought, well, wait a minute, now synchrotron radiation will cause this thing to spiral in the nucleus. As it turns here, it has to emit radiation, electromagnetic radiation similar to light, like light at different frequencies. And spiral in the nucleus, and it doesn't work. And so they had to come up with a new model. It got quantum mechanics. And even now, people don't understand quantum mechanics. The famous the Nobel laureate. Let me see which one I think is more important. The Nobel laureate Richard Feynman was famously said, if anyone says he understands quantum mechanics, he doesn't understand quantum mechanics. He basically said, I heard him on another occasion, nobody really understands quantum mechanics. So even so, there's this point where the mathematical model seems to fit, but the thing is that the mathematics, you prove everything, right? We proved all this. We start with certain axioms and assumptions, and with those assumptions, derive all this, and there isn't any doubt, you know. But once you apply it in a scientific model or something, then there's, well, does it really fit reality or not? I don't think. But nice thing here is we don't have to have so many opinions. We can just say, well, we proved it, right? And so on your test, it's either right or wrong, and you can argue with me, and we can find out a clear result, right? So now, here's some other ones. I'm just going to write these down rather than do more proofs. I want to say similarly from the other identities, we get the following. Now, I don't memorize these either. I'm just going to copy them down as soon as I can find them. Here's the other sum of the product identities. You can take cosine of x minus cosine y and rewrite it as minus 2 sine x plus y over 2. But you can see it's the same kind of substitution. Alpha, x equals alpha plus beta, y equals alpha minus beta in our other two identities, times sine alpha times sine x minus y over 2. So we can call that equation 5, right? And then there's some for the sines too. The sine, the difference of two sines, any two sines, sine of x plus sine of y can be rewritten as twice the sine of the sum over 2, the cosine of the difference over 2. There's how you can write any sum of sines as a product, times 2. Right? And finally, equation 7, the difference of two sines, sine x minus sine y, can be written as twice sine of the difference, sine of the sum. Wait a minute. Yeah. Sine of the difference, cosine of the sum, sorry. So these are hard to remember. They're pretty complicated, and they don't just easily derive from each other like the sum and difference identities did. But just be aware that they're there and be able to use those. Let's do an example of this one, why this one's important. This explains a very important phenomenon in the physical sciences, actually, called the phenomenon of beats. And it's used for other things too, but this is one of the big ones. I'm going to use t instead of x and y because typically in science what you do is have sine functions as functions of time t. You know, you have a propagating wave through the air and it's at a certain amplitude at a certain time and so forth, time and position. So I'm going to do this, or you have a certain frequency you're hearing and it's so many cycles per second. Let's do this then. Suppose I had two sine waves and by sine waves, remember the sine and the cosine make the same shape wave, just shifted over. How do you know that they make the same shape wave shifted over? Ever thought about that? I think I said it in passing, but don't write this down. This is just an aside. Cosine of x let's say pi over 2, 90 degrees minus x, or pi over 2 minus x is equal to sine of x. This is our cofunction identity. Remember this one? I hope that's the cofunction identity. Now the even identity says that instead of writing this angle, you can write minus that angle. It's cosine of minus that one is x minus pi over 2, the other order. And then think about your graphing strategy. This is the graph of sine, and this is the graph of cosine with the same amplitude and period. It's just that it's shifted pi over 2, right? You replace x by x minus pi over 2, it's just the graph. This is the cosine wave shifted over pi over 2 is equal to the sine wave. That's a proof, actually, that the sine wave is just the cosine wave shifted over pi over 2. If you take this one as the cosine and move it over pi over 2 units, just slide it over so their peaks coincide, they're actually equal for every value of x. So that's the proof, they're actually the same shape. For that reason, when I refer to either to a cosine or a sine, I'll just call them both sine waves, right? Two sine waves, whether it's sine or cosine. Now tangent is different, right? It's not a wave like that. When two sine waves of nearly equal period and the same amplitude, they don't have to have exactly the same. To get the full phenomenon, they have to be the same, but if they're close, you'll still see part of the phenomenon. Same equal period and same amplitude are added. The sum to product identity shows that you get the following result. We get a product with very different periods. This is the phenomenon that happens. I'll do it by the following example. And it displays beats. What we call them, where the sound, if you interpret these waves as sound waves, the sound goes on and off. If you call them electric current waves, then the current goes on and off. And so it occurs in electronics engineering, it occurs in acoustics, it occurs in vibration and structures, it occurs in everywhere you have waves. We're going to show an example here in a moment. So here's equation 1 applied. Let's rewrite, this is like a homework problem. Suppose I want to rewrite cosine of 4x plus, let's say 5x first. Cosine of 5x plus cosine of 4x as a product. Let's rewrite it and use that to sketch it. I said before that often it helps take a product and rewrite it as a sum. That makes it easier to sketch, right? Because you can stack them on top of each other. Just as true, when these numbers here, 4 and 5, are close, actually it's sometimes easier to sketch by rewriting the sum as a product. Because when they're close, they look almost the same. They just kind of gradually diverge, and it's hard to see how to add them up. You know, you don't have one just weaving up and down around the other like you did in the other example. So let's see what happens this time if I try and sketch it by rewriting as a product. And then the sketch reveals something very interesting. So, well, by equation 1, cosine of alpha plus beta is equal to twice the cosine of alpha plus beta over 2. So on the top we have alpha plus beta is 5x plus 4x all over 2 plus the cosine of the difference, cosine 5x minus 4x all over 2. Oops, I'm miswriting at times. I'm not writing this right. Cosine. Twice cosine, cosine. And this is by, it's not number 1, it's by 4. The one I just erased, sorry. By equation 4, cosine 5x plus cosine 4x is twice cosine 5x plus 4x over 2, cosine 5x minus 4x over 2. That's equation 4. Now, what does that mean? We rewrite it. 5x plus 4x is 9x over 2, so this is twice the cosine of 9 halves x times the cosine of 1/2 x. And now what do you notice about the periods of this one? If I were to take and graph just this part, this one has a large period, right? This has period 2 pi over b is 1/2. It had period 4 pi. So it only completes one period after about 12 units there. Pi is about 3. And its amplitude is 2. And so I can sketch that one. Start at 2, and it goes all the way down to -2, and all the way back up. And it takes until 4 pi, a little more than 12 units to do that. Right? Now what happens if I multiply it by this other function here? This will be the graph of y equals 2 cosine 1/2 x, the part I circled there. Oh, I forgot to put time. I was going to put t. I said, and I forgot. So think of x as time t. Anyway, so here's x versus y instead of t versus y. All right. This is this way. Now it's multiplied by cosine 9/2 x. This one has a much shorter period, right? This one, the period is 2 pi over 9/2, which if you multiply out, it's, let's see, 4 pi over 9. And it has 9 periods, right? This one has period 4 pi. This has period 1/9 of 4 pi. It has 9 periods for every one this one has, right? So it's going to go up and down real fast between plus and minus 1, right? The cosine oscillates between plus and minus 1. The result is if I draw this picture here, which is minus the other one, we'll call this one, right? This is the graph of this one flipped upside down, so it's y equals minus 2 cosine x. I have a pretty good idea what this product looks like just by taking this wave, the one that I have here with the long period, and multiplying it by something goes up and down 9 times as fast. So within this period, it goes up and down 9 times. So it goes like this. Something like that. That's about 9 periods. And now you see what is the phenomena that you're going to have. If this is a sound wave, right? A sound wave is a result of variations in the ambient pressure in the room, right? There's a certain pressure here from the atmosphere sitting in the earth. When you speak, your vocal cords vibrate the air and send out little pressure variations. And the ear is so sensitive, it can actually pick those high frequency changes up as it strikes your eardrum. Ear's a very amazing device. And it interprets them. Let's see if this is the pressure variation from the ambient pressure here in the room. The sound I hear goes off and on, off and on. It has a certain frequency you hear from this one, right? But it's going on off. And so you have this kind of weird sound where you're making actually 2 sounds, one at amplitude 1 and one amplitude 1, right? But the sum of the 2 sounds goes on and off. How can that be? Both of these are making a constant sound, like 2 singers. Two different. You can tell I can't sing. 2 different pitches, but when they combine together, the voices go on and off. Well, it doesn't happen too much in singers because singers don't tend to sing with pure sinusoidal waves. They have a jumble of waves that are coming out. That's why pitch is not actually real clear what it is so much as frequency. You can look at a frequency of a pure wave, but a voice that's a combination of waves. If you look at something called an oscilloscope, it'll show you the jumble of waves that's in a sound that comes in. Pitch, you take these different sounds and try and figure out what's the note that's coming out when they're coming out different waves. It's kind of hard to tell. You can tell when somebody's on key because they're generally the right frequency. But what you can do now is if you get something with a pure frequency like a tuning fork, if you strike a tuning fork, it's one of these things you tune your musical instruments, piece of metal in the shape of a fork like that, and you tap the metal down here and it vibrates pretty much close to a sinusoidal wave. Makes it sort of a pure note, and then you can tune your guitar or whatever you're trying to do, right? Well, if you take 2 of those that make roughly pure sine waves and strike them without the same loudness, right? But they're a little different frequencies. One's an A note and one's a C note or something. What you get is something that goes on off. And it's an amazing thing to see when you actually put pure sine waves together. And here's the video. We're privileged to see an MIT video this morning. Anybody can get it online. You just Google MIT phenomenon of beats, and you'll get this result. Let's see if I can do this here. Put this back. Hopefully people online can see this. This is also, this video is also going to illustrate something about antennas that I'll explain as we go along. So see, you get something for coming to class. You get to learn antennas too, even though I won't test you on antennas. Here's the phenomenon of beats. Hopefully it's going. Right? A slightly different frequency, but when you play them both at the same time, it sounds like they're going on and off, and that's the phenomenon of beats. So that's what you can do with these things, is explain certain phenomena like that. Let me stop this silly thing, or I'm going to play some commercial or something. All right.
Professor?
Yeah.
I just want to let you know, we weren't actually able to hear you during that.
Oh, no, you couldn't hear the sound?
We could hear the video, but not what you were saying.
Oh, okay. But you did hear the video, right? You said?
Yes.
Okay. I was saying that on the first experiment, what he's doing is he's got two tuning forks that naturally vibrate at the same frequency. When he taps one, the pressure waves it sets off through the air hit the other one and set up standing waves in the other one, and the other one starts to vibrate. You can stop the first one and hear the sound coming out of the second one, even though they never touched. So that was the first illustration. And then when he puts a clamp on the second one, so it vibrates at a little different frequency, he taps the first one. Now the sound doesn't transmit to the second one. You can't hear anything coming out of the second box for that reason. That's how antennas work. They only receive a certain frequency to create standing waves. So they have to be the same frequency to do that. That was a separate experiment than what we did today, just an interesting phenomenon by which we construct radio antennas and so forth. Right? You tune your antenna, and it changes the length at which electromagnetic waves coming in the form of radio waves coming through the air will set up standing waves in your antenna. And as you change the frequency of the antenna by lengthening and shortening the receiving length, you can tune just to one station, not get all stations at once. That's how that works. And the last part was the phenomenon of beats. I was saying when he's got them tuned to two slightly different frequencies and hits them both, then each of them makes a pure note, but at slightly different frequencies. Maybe one's an A note, one's a C note. And then the sound appears to go on and off, right? Even though each one is making a steady hum at one frequency, you hear the sound going woo, 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 right? On and off, because it's the phenomenon of beats. They appeared, their joint pressure variation looks like this, and it has a certain frequency. That's the tone you hear, but then it goes off and on and off and on. This being the amplitude is how loud it is. So that's what I was saying. I'm sorry that was hard to hear.
Oh, thank you for the explanation.
Yeah, you're welcome. All right. Well, the good news is then that finishes our identities. They put those at the end because they're the least important ones, but you need to know they're there, and you can see why. They do have some applications. But the rest of the time, we're going to start a new section, which is actually kind of a hard one. When we get through this, things will get easier again. But it's harder partly because you can't check things in your calculator, and partly because there's proofs involved in it. And so we'll spend a lot of time on this, doing lots of different examples. And this will be solving trigonometric equations.
Professor?
All this stuff we did with trig identities is partly so we can solve these trig equations. There are lots and lots of cases where the solution to some mathematical model involves solving these. So you have to be good at these. For instance, in calculus and everything beyond, they come up a lot.
Professor?
And what we're going to do here is going to build. It's going to start off not too bad, and it's going to get a little worse and a little worse. But it's not terrible. You just have to do the work. It's like, I like to give that example of ice skating I gave earlier in the semester, right? Ice skating is pretty hard. You have to practice that and practice it. Once you're used to it, it's so easy, right? Same thing here. Once you do a bunch of these, they're so easy, but you have to practice a lot. That's the thing. It's not like whatever history where you cram it down right before the test and you got it, right, for the test at least. If you don't keep up on the lectures here, get one behind, everything I say is gibberish, and then you've got a whole lot of catching up to do. So don't get behind on these. So we're going to do this. We're going to build gradually, start with simple trig equations and build up. So we build up gradually.
Excuse me, Professor?
Yeah.
We just can't see what you're writing right now.
Well, that's right. I do need to. Thank you. Sorry about that. Do that all the time. All right, we build up gradually. To be able to do these. And so I say this is like the house that Jack built. I can't remember the poem. I should bring it for my class is what I should do. You first solve one thing and building the first floor, and then this is just the thing that built the thing that did the thing that did whatever that Jack built. And so the first one is to solve an equation that's just of the form trig function of some sort equals a number. If you see an equation of that form, it's pretty easy to solve. Simply go or use the unit circle. And if it's not a special number, then you need inverse trig. That's why we just did that. All right, and it's best illustrated not by giving all the details, but simply by doing one. You see it. Here's an example. Suppose I want to solve sine of x equals 1/2. All right, find all solutions, not just one. I know one immediately is the inverse sine of 1/2, right? If sine of x is 1/2, one solution is x equals inverse sine. But what are all solutions? We need the unit circle. Here's how you can do it. You take sine x equals 1/2, sketch the unit circle, and then say, oh, you know what, let me not call it sine x, let's call it sine theta. Sine theta equals 1/2. Sine theta equals 1/2. I don't want to use x for cosine. And we'll say sine theta is the y coordinate on the unit circle. And so I need all points on the unit circle whose y coordinate is 1/2. Sine theta is the y coordinate. So here's 1 up at the top, halfway up. I sketch a horizontal line. That is the line of all points in the plane where y equals 1/2, right? Now sine theta equals 1/2. Sine theta is a point on the y coordinate of the unit circle. So I'm only allowed these points on the unit circle for sine theta to equal 1/2, which means that either I have this terminal ray or this terminal ray, and those are all the possibilities. Those are the only terminal rays that have y coordinate in the unit circle equal 1/2. Right? You find it by doing this picture. Now, over here, drop a perpendicular and construct the reference triangle and say, well, it goes from 0 to a half, so this side length is a half. This side is 1 because it's a unit circle, right? And so this side must be square root 3 over 2. You can prove it with the Pythagorean theorem, but since you've already memorized it, do it out of memory, right? This is a 30, 60, 90 triangle, and I observe that one solution of this equation is this angle 30 degrees, or let's do it in radians, pi over 6. Most commonly, these are solved in radians. For reasons in higher mathematics, when you do calculus, it saves a step at every calculus equation if you've done them in radians instead of degrees. All right. So that's one solution. Theta equals pi over 6. What are some other solutions you can see immediately? How about that? What if I want a whole rotation plus pi over 6, right? So I could add 2 pi. What if I did 2 whole rotations plus that? Twice 2 pi. 3 rotations in that. 4 rotations, 5 rotations. In general, I can put k times 2 pi. K rotations added to pi over 6 will still get me this terminal rate. So these are all the positions. K can be negative too. I can go a negative rotation plus pi over 6, right? Or negative 2 rotations plus pi over 6. But in general, pi over 6 plus k times 2 pi puts me at this terminal rate, and that's the only way to get there, right? This angle pi over 6 plus any whole rotations, where k, we say, is any one of these numbers, 0, 1, minus 1, 2, minus 2, etc. We call these the integers. K is an integer, we say. Integers are numbers with nothing after the decimal point. It's actually slightly different than whole numbers. What are whole numbers? Do you remember? I mean, you might think these are whole numbers, but technically in mathematics, the whole numbers are the non-negative numbers with nothing after the decimal point. So these are the whole numbers. Instead, I'll say this works for any integer because you want to include the negatives. So it's just a mathematical terminology. When I say integer, it means these numbers with nothing after the decimal point. Well, this is not the way people like to write things. You know, like if I say something weighs pounds 10, you say, wait a minute, you mean 10 pounds? Right, because you're supposed to put pounds after 10. Same thing here, when you write this, you're supposed to write pi over 6 plus 2k pi. That's just convention. So I'll say this is all the angles. I just interchange the multiplication order. It's the same, right? So here's a bunch of angles. But there's more solutions, right? Because there's also this terminal rate. What's that terminal rate? You have to think for a second, right? Always use symmetry in these to save yourself time. You could drop the perpendicular and construct the reference triangle and go through all these shenanigans. But really, if you think about it, by symmetry, this angle and this angle are the same because they come up to the same height, right? So this is also pi over 6. This is going to be the same kind of 30, 60, 90 triangle. That makes this angle that we're interested in. We're interested in what angles in standard position get you here. One is pi over 6. One is this angle, which is pi, a straight angle back up pi over 6. And then you want to rewrite that as a single quotient. So you say, well, pi is 6 pi over 6. And 6 pi over 6 minus pi over 6 is 5 pi over 6, right? Subtract the numerators over the common denominator. This angle here, pi less pi over 6 is 5 pi over 6. So the other thing is we could have theta is 5 pi over 6, and then we can go any integer number of rotations k, and 2 pi being a whole rotation, past there and land on it again, right? We could go a whole rotation plus 5 pi over 6, 2 whole rotations plus 5 pi over 6, etc. And then rewriting it so we don't make a mathematical faux pas, so to speak. We call this 5 pi over 6 plus 2k pi is the usual way we write it. Here are all the solutions. Pi over 6 plus 2k pi and 5 pi over 6 plus 2k pi. And here's another thing to keep in mind. Again, this is what you get coming to class instead of just doing things out of the book. What's wrong if I put and here? It's a real technicality. If you put and, it'll probably give you full credit in your test. But because I know what you mean, that these are all solutions. These are solutions and these are solutions, right? But technically, you might say and, that means that theta has to be both. How can theta be pi over 6 and 5 pi over 6 at the same time? It can't. And means it has to satisfy both equations. So we write or, meaning it can satisfy either equation, right? So use or, not and in there. Otherwise, I probably won't count any points off, but I'll scratch it out in red and put or. So, anyway, there's the set of solutions. These or these comprise the solutions. Any questions on that online or in class? That's the basic example right there. That's what we're going to do with a simple problem, trig function equals a number. You simply draw the unit circle. If this number comes from a special angle, like 1/2 does, then you can just figure it on the unit circle. If it doesn't come from a special angle, we're going to do that later. You have to use inverse trig. But you can still get all the solutions in terms of an inverse trig function. Nice. Well, there's a little harder example. Suppose I said solve tangent theta equals minus the square root of 3. How about that one? By the way, sometimes you'll see me put these parentheses on because tangent is a function, right? It's like f of x. But sometimes you'll see me leave them off because books often do that too. Everybody knows it's a function. To save writing, we sometimes don't bother to put our parentheses. But the idea is this: don't make this mistake on your test, right? If I put tangent of 2 theta, you can't pull that 2 out. It's not 2 times tangent theta. You can't pull it out like that. The idea is that there's parentheses here. It's 2 tangent of 2 theta, like f of 2 theta. You don't just pull the 2 out of here, right? It's not multiplying f, it's f of that number. So I won't always write the parentheses just to save writing, but there are implied parentheses there. It's a function. And people do that on a lot of functions. So tangent theta is minus square root 3. How do I solve that one? It's harder because sine was the y coordinate. I could just draw this horizontal line, but alas, tangent, not so, right? Tangent is y over x. So all right, tangent theta equals minus square root 3 is supposed to be y over x on the unit circle. So I know what I'm doing, right? Minus square root 3 over 1. Now it's y over x, right? Is this y and this x on the unit circle? I'll give you a hint, it's not. I can't say this is y and x on the unit circle. What would be a point on the unit circle that has that ratio? Right, this is too big. This is minus 1.7. It's outside the unit circle, right? And this is 1, so you're way outside the unit circle. Do this, divide both of them by 2. This is the same as the ratio minus square root of 3 over 2 over half, right? But this, by memory, is a point on the unit circle. Now I can treat this as y, and this is x, a point on the unit circle. But there's a trick here. What's another ratio that's equal to this? Instead of dividing top and bottom by 2, I could divide top and bottom by minus 2 and get the same ratio, right? I could get square root of 3 over 2 on top and minus a half on the bottom, putting the minus down here. So this could be y and this could be x, right? And both of them work. Both of them have a ratio minus square root 3. And those are both points on the unit circle. So what we get is this. We go to plot the point. Y equals minus square root 3, x equals a half on the unit circle. Again, when you solve trig equation equals a number, a trig function equals a number, you sketch the unit circle. For sine and cosine, you plot the horizontal line, y equals a number, or the vertical line, x equals a number. But for tangent, you have to treat it as a ratio of y over x. We'll do this. Suppose y is minus square root 3 over 2. It's like minus 0.87, something like that. Here's minus square root 3 over 2, so it's almost minus 1. 1/2 is halfway. 1/2 is halfway to the right here, and we're going to go through this point. So here is the one angle right there that has y equal minus square root 3 over 2 and x equal a half. But there's another one, y could be plus square root 3 over 2 here, and x could be minus a half. Now, this goes through this point, directly opposite. How do you know it's directly opposite? this minus y becomes plus y, this x becomes minus x. X and y are just minus each other, so it's straight through the same distance the other side, right? So they're always opposite. That's something to remember on tangent and cotangent. Those two are the hard cases, but their solutions are always directly opposite. So there's the two terminal rays that I need to get this ratio and get a point on the unit circle. This isn't on the unit circle. I'll give you a hint. We'll do this later. But the number you have to divide by, I mean, you recognize it. These are on the unit circle, square root of 3 over 2.5, and any other ratio isn't. You have to divide this top and bottom by the root sum square of these. Square root of minus square root of 3 squared plus 1 squared is square root of 4 is 2. That's what you have to divide top and bottom by to get a point on the unit circle. If you don't, then x and y won't be on the unit circle. This makes this one squared plus this one squared equal to 1, so it's on the unit circle. Anyway, so divide top and bottom by the root sum square, and you'll get this a point on the unit circle. Now I can recognize this, right? If this is, I can draw a reference triangle now. Oh, it's 1/2 square root of 3 over 2. That's a 30, 60, 90 triangle. That angle must be 60 degrees, pi over 3. But that's not the answer, right? The angle of standard position that goes there, that's just the reference angle. The angle that goes there is pi back up pi over 3. So you write that to get a common denominator, 3 pi over 3 minus pi over 3. Subtract the numerators, 3 pi minus pi is 2 pi. All over the common denominator, 2 pi over 3, right? So there's the angle that goes to this terminal rate, 2 pi over 3, and then you can add any number of whole rotations to it. How about this one here? What's that angle? You can use symmetry. And I could do this. I could say, oh, let's see. This is 30 degrees, so this must be 30 degrees, and I've got 90, 180, 270, and 30. It's 300. Okay. And then convert that to radians. You can do it the long way or easier. I think when it's close to a whole rotation, it's easier to say by symmetry, if this is pi over 3, this is pi over 3, right? That being pi over 3, the angle I want is a whole rotation, 2 pi, less this angle, right? 2 pi back up pi over 3. Now I write 2 pi as 6 pi over 3, multiplying top and bottom by 3. I go 2 pi over 1, multiply top and bottom by 3. Subtract pi over 3 to get a, now I have a common denominator. 6 pi minus pi is 5 pi. That's all over 3. So there's the other angle. There are two angles between 0 and 1 whole rotation. That's what you do. You find an angle within one rotation of both terminal rays. 2 pi over 3, 5 pi over 3. Then I've completed one rotation. After that, you just add whole rotations to that. So the solutions are these. Theta equals 2 pi over 3 plus k whole rotations is 2k pi. Theta equals 5 pi over 3 plus k whole rotations. There's all solutions. And I'll give you 100% on the test for that, because that's all the answers. And here k is supposed to be any integer. It's 0, plus or minus 1, plus or minus 2, etc., and so on. What's a more compact way to write that? You see it? This is all the answers, but you can write that in half the work. Really clever here. Hard at the end of the period. I used to have my afternoon classes when I was an undergraduate. I'd give this 3 o'clock class and be warm, and I'd just be dozing back. I couldn't think anymore. Fortunately, we got a morning class here. What you can do to combine them is think of them instead this way. So alternatively, do it this way. When the angles are straight, when the terminal rays are straight opposite each other like that, do this, construct the first one. Theta is 2 pi over 3, this one, and then say instead of going whole rotations, I can go a half rotation, half rotation, half rotation, half rotation. Any integer number of half rotations. I can also go backwards, right? Half rotation, half rotation. So it's pi over 3, the first one of the two. You don't even need the second one. Plus k half rotations. K times pi is a half rotation. And that's it. K equals any integer. That's right, half the effort. So that's what you do when they're directly opposite. You write them compactly to save writing. This is also correct, easier, right? Do that when they're directly opposite. Find one angle, add K half rotations with K any integer. Questions on that one? See how tricky this is? This is the first one. This is the easy one. I don't want to scare you. It's not, I guess it's not that bad. You just have to do it carefully, like you learn to ice skate carefully. You don't go real fast and crash hard on the ice the first time out, right? Well, build things up slowly, you're going to do real well. All right, so that's how to do those kind of things. Suppose I did this one. Suppose I want to solve, I'm going to throw a little wrench in the works here. Secant of 2 theta equals minus 2 over square root 3. Oh boy. Huh. How about that one? Now I've got a secant. We did a sine, we did a tangent. Now we're going to do a secant. How can I solve that one? Here's a trick. If only it was cosine, I could solve it, right? I know how to do that one. Make it so, right? If these are equal, their reciprocals are either equal. Whenever you see secant or cosecant, just rewrite it as reciprocals. Cosine 2 theta must be minus square root 3 over 2. There it is by reciprocal. Now I can solve it. But I said I threw a wrench in the works. You see a little difference from the previous problem? Instead of cosine theta, I have cosine 2 theta. How do I solve it when it's 2 theta? Again, when it's not what you want, use the Carr's rule, right, and make it so. You call 2 theta alpha, and you rewrite this. Let alpha substitute be equal to 2 theta, and write cosine alpha equals minus square root 3 over 2. So don't worry if it's a secant or a cosecant, just turn it over. Don't worry if it's not theta, but a multiple of theta, just make a substitution. Now I can solve it, right? If I solve for alpha on the unit circle instead of theta, I can do it. And then theta will just be 1/2 alpha. So that's how it works. Cosine alpha equals minus square root 3 over 2. Now we're doing a cosine. The cosine is the x-coordinate. So I sketch my unit circle. And then I put all x coordinates minus square root 3 over 2. Again, that's about minus 0.87 or so. So way over here, almost to minus 1. These are all points with x coordinate minus square root 3 over 2. And there's 2 intersections in the unit circle, right? Since it's to the right of minus 1. About there and there. There. And so there's exactly 2 terminal rays that can give me that x coordinate on the unit circle. Only 2, right? So again, I'll find all angles with the 1-1 rotation that go to those terminal rays, and then I'll add 2k pi to each, and I'll have all angles that can go to those terminal rays. Hate these maths. I keep telling my classes that sometimes these things do more harm than good, especially kids. You put them on it, have to get adjusted all the time like I do. So I was putting their hand on the doorknob and then putting their hand on their mask, putting on the rail, putting on their mask, put everybody's germs right in their face. I'm trying not to do that, but I keep it on. All right, so those are the 2 terminal rays. What angle is that? Well, you look at it and say if the x coordinate is minus square root 3 over 2, then this side length is plus square root 3 over 2. I'll say this is the x coordinate, but this is the side length is the absolute value of that. Lengths are non-negative. Now, if this is 1 because it's a unit circle, oh, this must be a half. It's a 30, 60, 90 triangle. This angle over here is in fact pi over 6, we observe, right? That's pi over 6. Then from the other example, pi back up pi over 6. This must be 5 pi over 6, right? And similarly, you apply symmetry, right? Since This is the same base and the same hypotenuse. This triangle and this one are congruent. All right, so you just flip this one over. This must be a pi over 6 angle by symmetry. Don't go figuring it all out. Just say, oh, it's obviously symmetric. There it is. And that makes the other angle we're interested in equal to what? Pi, add pi over 6, right? Is 6 pi over 6 plus pi over 6. Add the numerators over the common denominator, 7 pi over 6. So there's two angles, 5 pi over 6 and 7 pi over 6 within one rotation. Right? You go all the way around to here and around to here, there's two, and you get to one rotation. You just take those plus 2k pi. So the solutions here are now theta equals 5 pi over 6 plus 2k pi. Theta equals 7 pi over 6 plus 2k pi. And I can't write these combined because they aren't straight across from each other. There is another case where you can combine. We'll get to it later. If you get like 4 of them all symmetric, you can do this one plus 90 plus 90 plus 90. So you can do that kind of stuff too. But unless they're symmetric all around the circle like that, you really can't combine them. So we'll just leave these like that and say that's all solutions. Questions on that one? There's all solutions to a secant problem. All right. Well, I'm just about out of time, but maybe I'll just mention this one. Step 2 is this. Suppose I wanted to solve a number a times a trig function plus a number b equals 0. How would I solve that one? This actually comes up a lot in mathematical modeling and lots of equations. You never get trig function equal to a number, you get it in this form. What do you do with that?
Professor?
Apply algebra to write it as trig function equals a number. Apply algebra to get it in the form trig function equals number. In other words, you subtract b from both sides and write it equivalently as a times trig function equals minus b and divide by a, and you got trig function equals minus b over a number. And now you go to step 1. There's the house that Jack built that I was talking about. You subtract b and divide by a, and then you go to number 1. I won't have time to finish the problem because we're just about out here, but let me just make an illustration starting with. And we'll do these next time. But example, suppose I said solve 2 cosine x theta plus 1 equals 0. How do I solve that? It's very easy. You subtract 1 and get 2 cosine theta equals minus 1 and divide by 2. Cosine theta equals minus a half. Now you go to step 1 because you have trig function equal to number. I guess maybe I have time to just write it real quick. Next time we'll do these in more detail. Cosine is the x coordinate. So I want all points with x coordinate minus a half. Right? When I sketch those angles, there's only 2 of those terminal rays, there's only 2. With a little work, you'll see that this is 2 pi over 3. Well, a little work, you'll see that this is pi over 3, the reference angle. Means that this has to be 2 pi over 3. And by symmetry, if this is pi over 3, this is pi over 3. So this is pi plus pi over 3 comes out to be 4 pi over 3. I'll spend more time on these next time. And your solutions are 2 pi over 3 plus 2k pi, any number of rotations, or 4 pi over 3, the other terminal ray within one rotation, plus 2k pi. So there's what you do when it's that. You just apply a little algebra and then go back to solve the trig function equal to number. Let's just try this one. Do all the problems out of the section 7.4 on the UCO supplement. And then on 7.5, try number 1. I think that's what we can do. Let's see. Number 1. No, not number one. Number one's the one I deleted. It's all bonus. Sorry, it's number two. Yeah, you can do number two already. Right. So, actually, you do 3A. So let's start on those. I'm going to give you all of them on 7.5 if you want to work ahead, but you should be able to do these now. Try those and bring questions, okay? I'll do a lot better for you if you bring questions so I know what's hard. Thank you for your attendance. Please like your desk.